Hello. We're going to try to replicate the sound of a wave by sampling its line spectrum and constructing a sum of pure tones with amplitudes and frequencies taken from sampling the line spectrum. Now there's some potential difficulties in doing this. First of all, the line spectrum is based on the whole sample. For example, we're going to work on the C1 key from my Cumulative grand piano. It's sampled at 44 kilohertz, and the sample is around 5 seconds long. So the line spectrum is going to be constructed from that, and therefore it will not be able to key off of any trancing effects, such as the short period of time after the key is struck, as compared to the time after the key has decayed its sound. So it's going to take all of it into account. So it's kind of an average effect. We're not going to take into account any of the phase information, because the line spectrum is in fact the magnitude of the Fourier transform. We're going to replace peaks of varying width with isolated spikes at the frequency of interest. And we're going to be ignoring any spurious components in between the peaks that we pick. And finally, the sound system I'm going to use is a combination of my inexpensive laptop speakers with and laptop microphone with the Cam Studio system. So what you hear may not be particularly high quality. Now, each time we pick a peak, 3 sounds will be generated. First will be the pure tone at that peak, at that frequency. The second sound will be the sum of whatever pure tones you've accumulated up to that point. And then third, we'll hear the sound that we're trying to replicate. Okay, let's get started. Here's the line spectrum of the Cumulative C1, and I'm going to take a look up to about 2,000 hertz. I'm going to try to sample all these spikes in here. We're going to sample 5 spikes, 5 peaks at a time, 5 frequencies. So here's the first 5. Okay, let's go down here and start at the lowest, which is around 32 hertz. You won't be able to hear this because the speaker just can't deal with 32 hertz, but we'll do it anyway. Here we go. Okay, the first 2 sounds were hard to hear, if you could hear them at all. And that was the sound of this pure tone at 32.7 hertz or thereabouts. The second sound was the sum of all the tones we've accumulated, which in this case is just 1. And then the third sound was the actual wave we're trying to replicate. Here's the second one at around 65 hertz. Okay, the first sound you heard was the sound at 65 hertz, which was barely audible because the speakers can't handle that frequency. The second sound was the accumulated sounds that we've done from the first 2 samples. It sounded exactly like the one at this particular frequency because this one is so weak over here. Third sample, the third peak. Okay, once again, the first 2 samples are pretty similar because these 2 are weak. Move on to the fourth. Okay, now the second sound was different from the first sound. and it was a little bit like the sound we're trying to replicate. Okay, let's move on to the next set of 5. Now as we add these tones, these pure tones, see if you can hear its presence in the sum of whatever we've accumulated so far. You could almost hear it in that last case. Okay, this one's not going to make any contribution, but I'll add it just for the sake of completeness. Might be able to hear this particular tone in the second sound. Actually, I couldn't hear it, so let's move on. Okay, here we go. Now I could actually hear this pure tone in the second sound this time. I could almost hear it in the second sound this time too. Hopefully you can start to see or hear that the second tone is starting to be a little bit like the sound we want to replicate. And it's because these higher frequency partials are actually making a significant contribution. Partial, I could definitely hear that in the second sound. Okay, let's do 5 more and then we're going to skip. Starting to sound a little bit like the wave we want to replicate. Now, for example, here we're going to ignore this little peak and also this little peak here. Not that it would make a difference. Okay, we have accumulated 25 partials. We're starting to sound like the wave we want to replicate. I'm going to skip ahead now. I'm going to actually continue sampling all these peaks and including them and adding them in, but the video will skip ahead until we get near the end, just because of time considerations. Okay, we're back, and I'm going to continue. We've done 40 partials so far. Now we're going to start on the let's see, 41st right here. You see, you're starting to accumulate a sound that is pretty close to what we want to replicate. And you also notice we're going to ignore all these extra spurious peaks in here. Notice we're probably in the area of diminishing returns because you can't really tell much difference as we start to add these last. Now here's, for example, one where the algorithm suggests this is where we should be sampling, but in fact it's right up here. I'm going to pick this one. It's not going to make that much difference. Okay, we're getting near the end. Okay, here's the last one, which is of academic interest only. Okay, we've got 50. Let's see what this thing does for us now. Okay, here is the line spectrum of our starting wave. Here are the samples that we just finished accumulating. Okay, here it is again, bigger scale. So we have gone through and sampled that wave, that line spectrum of the original wave, and we have constructed this particular sound, or this particular spectrum. Okay, those are the two tones. The first one was the one we constructed, the second one was the original. Or it could have been the other way around, I'm not sure. Here's the picture again plotted, this time in decibels, of the original wave that we're trying to replicate and the constructed wave. Again plotted in decibels. This time I'm plotting the original wave in decibels, its line spectrum, and down here I'm plotting the line spectrum of the constructed wave, not the samples, but what actually is constructed. And you can see it's similar. For example, there's a lot of activity here in this wave that is not down here. So all the spurious stuff like this stuff in here, does not show up down here. Here's the cumulative line spectra of the two waves, and they're pretty close. The autocorrelation of the original wave and of the constructed wave are fairly similar. This is the largest peak here, and it does not correspond to the fundamental. Let's see what it actually is. It's around 60, let's say 61 milliseconds, so that corresponds to a frequency of around 16 Hertz, so that's the subharmonic, this peak right here. The other peak, which is usually showing up around here, this is at about around 31 milliseconds, which corresponds to .32 Hertz. So this little doublet here, which occurs in both cases, is related to the first partial. Here's the spectrogram of the two signals. You see the difference here is that the original signal has got a lot more components, and the signals die away. See how the components die away here? I'm plotting the spectrogram. This is the power versus frequency versus time along this axis. And so here's the first partial, which is, well, not the first partial, one of the early partials, which dies away. On this constructed curve, they don't die away. They have the same magnitude throughout the time period. Okay, that concludes the presentation. We have tried to show how to construct a wave that mimics the original wave by sampling the line spectrum. Thanks for watching and listening.